So hello, this is our DA project, a network traffic cancellation model using UMAP, Smotomic, and stacking classifier ensembles. This is the complex data that we will be using, which is the CIC IDS 2017. The type of it is a multi-class type, has eight files, and over 2.8 million instances, 79 features, and 15 distinct classes. This is the pie chart which show the distribution of the classes. Here is our exploration of these data. It had missing values around 0.05% of the whole in information. It has some zero variant columns, and it had duplicate loads, which is 10%. This is the table showing the unique level in the data that we'll be using. Here and in here we encounter a problem that the data has an imbalance class. Even after we grouping the minority class, which this could lead to us having a false prediction using this our part of doing the pre-processing. We use the technique of sampling called stratified sampling, which is the sampling that will remain the original percentage of each type of each class of the data. Next, we're going to use UMAP for dimension reductions. As we said before, that this data has over 79 columns. So UMAP works by constructing a high-dimensional graph, and then they're trying to cut the dimension and then optimize it in a low-dimensional graph. Next, we'll be using Smotomic. As our class has an imbalance problem, we use Smotomic to generate a synthetic instances. Like here, the left picture is the normal Smooth, but now we combine Smooth with Tomic links, as shown in the right, which is the Tomic links. Here is the data visualization before Smotomic. As you can see, for the web attack, there are very few of them. And after we use the Smotomic, yeah, you can see a lot of blue lines coming up.
Next section will be the analytic techniques. Okay, for the predictive analytic, we will use the stacking ensemble model or a stacking classifier. Okay, so stacking ensemble will use the meta learning algorithm, which is there will be a model called meta model, which will learn to combine and assign the weight to the base model predictions in order to get a great final predictions. The advantage of using stacking ensemble is that the stacking classifier can learn the key advantage of like various model and properly combined to get more accurate predictions compared to like a single model. And let's say it's architectures. In the level 0, there will be a list of base model. Base model can be like support vector, machine, logistic regressions, can be any model. And this model will get trained on the dataset, and they will output predictions. And those output predictions will get to be trained by the meta learning model, which just can be any machine learning model here. And this meta learning model will output a final predictions. And here, let me introduce the list of base learning model that we will use. First, we use XGBoost classifier. XGBoost is a assemble machine learning algorithms that combines multiple weak learners, which is a decision trees, and create a strong predictive model. It iteratively train or add on the new tree to the assemble, with each tree will be focusing on fixing the residuals or error making by the previous tree. And it is quite different from the random forest because random forest will use a backing algorithm, which it will have like multiple decision trees and train on the model, and at the same time, and they will evaluate the output for the final predictions. But for XGBoost, it using boosting algorithm, it do in the state-wise manners. Okay, and another algorithm used for the base learner in my architecture is the CatBoost. CatBoost is very similar to the XGBoost. It uses gradient boosting, as I said earlier. It is the assemble of decision trees trained sequentially, and but the key difference is that CatBoost is made to handle the categorical features internally. You don't need to encode it if you use the CatBoost model. Okay, and CatBoost also use the order boosting technique, which is just it will like sample a random sample of the training set uh, for the new decision tree to train on. And another property is symmetric tree. It's just that it will use the same criteria for splitting the node to create a subtrees. Okay, and let's go to our stacking classifier architectures. Okay, for the base learner, we have XGBoost, CatBoost, and this one is the logistic regressions. And for the meta model, we have the random forest. The random forest will get trained on the base model predictions and learn to assign a great weight for the final predictions. And let's see some evaluations. Okay, so I combine the single model CatBoost with the stacking classifiers according to the architectures. Okay, let's see. So the overall accuracy is 95% for single CatBoost, and overall accuracy for the stacking is 90%. Okay, and you can see for the class that have like low support like botnet and web attack, you can see it get low F1 score like 23 and 64. But if you see as a stacking classifier for botnet and web attack, it get 33 and 87, quite higher, quite a increase. Next part will be the demo. And okay, here's my code right here. So first, right here, I just mount the Google Colab with the directory that contain the dataset. Here I import library, and as I said, the CIDS dataset consists of like 8 CSV files. So here you have to join it first to get the final dataset. You can see it have like above 2 million rows, quite much. And here I do some basic EDA. Okay, and here's the stage that I try to clean the data quite a bit. First, I do new value analysis. This kind of step already like assess on the first part of the presentations on the pre-processing. I find duplicate rows, and here is a CleanDF functions where I remove zero variant column. I remove duplicate, remove row with NA, and remove identical column. Here's a function that I groups list of like class label into main main category. Yep. Okay. And here is the we have 6 class now after grouping. Okay, and I do certify random serving since we have like 2 million data. Colab cannot train it. Okay, so I sample 10% of the data while maintain the same distribution of the class population. I get 10%. And you can see they have like very the same distribution as original, but in the lower volume, of course. And next, I split the dataset. I scale it. I use UMap for dimension reductions to 25 components. And here I do class balancing with smooth atomic. Okay, so here's like before smooth, here's after smooth. It's balanced now, you can see. Look balanced, okay? Look very similar couch in each class. And here's nothing. This is just a part that I do some evaluation. Here's a part that I use like only cat boost here. You can see here, and I do some predictions. The result is same as the one on the page of presentations. And here's the code of this stacking classifier evaluation. So you can see that here I define a list of the base model, is same as the architecture that I said earlier, and the meta model will be random forest. And here you use a stacking classifier class from the sklearn. You can see you can set the list of base model, and the final estimator will be of course our random forest here. And you just fit it to the data, to the training data in the same way, and you can predict it. And this one I just put some classification report and some confusion metric, and that's all. Go back to the slide. Next section is a list of possible applications. Okay, so you can use it in the intrusion detection system if you scale it up, and you can use it for the network monitoring and optimization for customer behavior predictions. You can use it for like classifying like wow what type of like software service that user is using, like is he using YouTube, Facebook. And another thing is like healthcare and medical diagnosis. Yeah, and you can use it for fraud detections in financial service, because like this kind of data set usually is not balanced, and they usually contain many features. So maybe you can try like dimension reductions and so on. And you can do it for predictive maintenance in manufacturing, because like this kind of data set is usually like imbalanced. Okay, so here's a list of reference. For the reference for data processing, we have like this one. And for the modeling part, we have like reference of cat boost, XGBoost, and it's come to the end of our presentations. Thank you for listening. Hope you enjoyed.